these are the equations we just came up with. So if we would have done node n, you can see how it ends up. It's important to note, we have to be careful about what we're doing on node I. Node I is for the center nodes, is only between 2 and n-1. And then we have these other two boundary condition equations. Right, and again, if we had something like a fixed temperature at node n, this would go away, and this would just be Tn is equal to Tc or something like that. Okay. So this is our set of equations. What we're going to do now is just look at this in ease. Okay. Okay, so a couple things to point out here. I haven't talked about this yet, but these statements up at the top, these are unit settings and kind of tab format settings. So if you could go in every time you go into ease and set, click on the units. Let's see where the units are here. So I could go down to the bottom here and click this. And it'll pop up and let me select my units. If you don't want to do that, or you want the units you're using to go with the file you're developing, it's really helpful to give these unit settings here. So this is just saying units are an SI. We're using mass. We're using joules. Right? These are just all the settings that you can choose. So that directive is useful. The other thing is this tab stops thing. This tells you if you hit tab where the character stops, like how far across the page. So when we get into problems like this, where you have duplicate loops, maybe it's a 2D problem, you've got nested duplicate loops. If you don't set up the tab stops, your formatting can kind of look weird. So this is just a way to have the file formatted the way you want it to. Okay, so now we're entering information. This is just all the stuff that was given in the problem. Contact resistance, temperatures, diameter. We've entered a diameter both in terms of the unit we care about, centimeters, and the SI equivalent. Just as a matter of practice, it's good to use SI equivalent or SI units pretty much throughout your entire programs. Just makes things easier. Okay, so that's all the information. Here's our cross-sectional area. This is pi d squared. So this is the cross-sectional area available for heat flow. It's the diameter of the wire, that cross-sectional area. And then this is the interesting part now. So this is the numerical solution. So the first thing we do, we're going to say how many nodes we're going to try to model this with. In this example, can you guys see this okay? Or is it too small? Good. Okay. In this example, we were just going to use 11 nodes to start. So that's probably on the low side of the nodes you'd ever want to use. For this example, it ends up being okay because it's relatively stable solution. But you might find that you're going to have to use 100 nodes or 500 nodes or something like that to get convergence in your solution. If you're finding that you're getting 500 or 1,000 nodes or something like that, eventually ease is going to say, sorry, you're not giving me enough money to do this. And you're going to have to do something else, right? So you could go buy the professional license and expand your number of variables, or you could just say, okay, thanks, ease, I'm going to do something else. And that's what we'll do in this class. We'll get to a point where, like this, today we'll talk through ease. This is one way to solve these kind of simpler numerical solutions. But really, for most of the stuff for numerical solutions, we're going to want to use something like MATLAB. Okay, so we chose 11 nodes. That gives us a nice, n-1 gives us 10th steps. So that's why we have 11 instead of 10. Okay, and then we use this expression duplicate. So I don't know if you guys have seen this before, but what duplicate does in ease is it takes whatever you put inside that loop and it repeats it however many times you tell it, substituting the thing, the index that you're giving it as an argument. Right? So here you say duplicate I equals 1 to n. So what that's doing is it's taking whatever you put in the middle there, is duplicating that equation in ease, in ease's kind of equation setup n times, but then only substituting out I each time. Right? And it's really important to actually think about what I just said there. So you could put in here something like this, where we'd say just x is equal to this. Right? And what would ease do if we could try it. What would ease do if I did this? It's going to complain, right? It says I got 36 equations and 26 variables. So what I've actually done is I've repeated the same equation for x, 10 times or 11 times. Okay, so It doesn't like that. It can't solve it. So we need to kind of be careful about what, you can't just include everything in that duplicate loop like you could in MATLAB or whatever. Here you have to be really careful about what you include there. Okay, so duplicate that. This sets up our domain for X. Here we compute the dx length. And then the first thing we did was internal nodes, right? Internal nodes, this is our equation. If we flip back and look, right, so our equation was KAC T2 minus T1, or sorry, internal node TI minus 1 TI. Right? You just look at this, came up with a solution for I equals 2 to n minus 1. So we look back at ease. What are we doing? We're duplicating for I equals 2 to n minus 1 for this exact expression. You can look at it this way, right? This exact expression that we derived, this one here, right? So this should look exactly the same as what we did to just derive it right now. Note that we don't have to be explicit, like we have T's, Ti minus 1, Ti, I plus 1, they're all mixed in together in this equation. Ease is very happy to solve that. Like it doesn't care that you're not explicitly solving for things and assigning them. So it's very happy with that. Okay, so that's for the internal nodes. For the node 1 and for node n, you can see what we're doing here. Just we'll look at it in the code again. So here we are using t at the index we specify, right? And entering equations for that. And we end up with our system of equations that has n equations and unknowns, and we should be able to solve it. So if I check this, Control K, 36 equations, 36 variables, and we should be able to solve it. So I'll solve this. It solves, hooray. And now where's my answer, right? We put everything in a duplicate loop, so now where did the answer go? We have some information, those constants like that we entered, the temperature, but we don't have available, on this page, the actual answer. What you need to do is go to Windows, Arrays, or Control Y. Okay, and this is going to give you anything that you've entered as an array variable with the square brackets. That's all going to show up here. Right, so now we can see, yeah, okay, we got X, we have the temperature at any position X, and it kind of looks like, just staring at numbers, I guess it kind of makes sense. We have temperatures that are between the two temperatures we specified, the hot and the cold. It's decreasing as a function of position. So we went from X at 0 on the hot side to something much colder on the bottom. And so, it's kind of making sense. The other thing we can do is plot. So let's generate a plot of this temperature. So we'll go to Windows Plots, or Control-Alt-1 is the shortcut there. So now we have our temperature, right? So this is telling us that as a function of position, actually my hottest temperature is not right at the hot boundary. It's somewhere in the middle. So you're seeing that there's an effect of conduction in the axial direction that's an important part of this problem, right? So yeah, this is the solution for this problem. So we can do some interesting things with this. It's not just plotting the temperature. So let's say we wanted to use this program to figure out the optimal diameter. But as you make the diameter bigger, you're going to have more energy generation. As you make the diameter bigger, you have less energy generation because the current density is lower. But you have more material to conduct. So there's some trade-off that you might have where there's actually an optimal diameter for this problem. So what we could do there is we could go back. Let's see. So we comment out our diameter that we specified here. Oops, how did that happen? So we comment our diameter we specified here as D is 0.7. That double backslash is another way of commenting a whole line. And then we're going to go create a new table. So go to the tables. And I already entered this in, but you click this little guy. You should have probably done this on homework already. Enter your values, populate the table, and then solve it using this arrow or F3. And we now get back, oops, sorry, what am I looking at here? Yeah. We now get back heat flux out of the bottom of this wire. Right? So what we're trying to do is minimize or pick the diameter that minimizes the heat flux out of the wire. Okay? We don't want conduction to be happening through the wire. We just want electricity moving through the wire. Okay, so we've done this. We can plot it and it looks something like this. Okay, so we see actually there's a diameter of the wire that corresponds to the minimum amount of heat flow from the hot to the cold due to conduction. I'm sorry, I wasn't very clear about that up front. What we're trying to do is pick the optimal diameter so that we're minimizing the amount of heat that's going into the cryogenic load. I should have said that first. But here we are. So we find that, yeah, there's a diameter for that. And we can solve it using this problem. You might go back and try different nodes and make sure that number of nodes and make sure it's all converged and everything. But this is kind of the general approach for numerical solutions. Okay, and the last, sorry, any questions on that? Okay. Let's see, the last minute here too. I think what we'll probably do is save most of this for next time. Yeah, so what we'll talk about next time is how you actually do this stuff in MATLAB.